Hey everyone. So this is going to be your guided climate notes for the first part of this lesson. Basically, we'll get you up to around slide number 10, and then from there, you'll do your exit pass. Tomorrow, we'll finish up the notes together, and then you'll have access to the filled in version. So we've done the water cycle. We've done air masses and fronts. This is the last part of our unit on weather and climate, which is climate. So as we go through this, your job is only to listen. You don't really need to do anything else. You can take notes on the side on paper if you want, but because we're doing the exit passes, I'll be able to see if you have any questions or how well you understood everything. And again, if you have any questions, you can always put them in on the Google assignment comments, and I'll be able to answer those. So we'll get started. So climate, again, we're going to talk about why it's different than weather. So we talked about the water cycle, we talked about weather and how we forecast the weather. Now we're going to take a look at climate. And basically, climate is a long-term average of weather. So weather is more day-to-day, hour-to-hour, it changes frequently. Climate, on the other hand, is the long-term average. So basically, it's weather over time. And we look at climate based upon a certain location. So for that, we're going to be looking at the same characteristics as weather. We're still looking at temperature, we're still looking at humidity, we're still looking at wind speed and direction, we're still looking at the type, the quantity, and the frequency of precipitation, but now we're looking at it over time. On average, for this location, how much rain do they get yearly? Or how much rain do they get for the month of April? So again, for climate, we average these things over time. It's weather over time. So typically when we talk about climate, and of course you guys have heard a lot about climate change, we've learned that climate does change, but typically it happens very steadily. It happens slowly, not drastic changes are occurring. Of course, of late, we have been noticing that there has been a lot of change quickly, and that's what's causing concern for scientists. And that's why climate change is a better term instead of global warming, because it refers to the anomaly that's happening, which is instead of changing slowly, now it's changing quickly. So although we're not really necessarily getting into climate change for this lesson, there's a bunch of things that I could send you if you're really interested in it. Especially now with our COVID quarantine. There's been a lot of information put out kind of comparing the amount of carbon dioxide and emissions put into the air pre-quarantine versus post, when everyone is staying at home and traveling less. It's just interesting to see. But in general, climate changes very slowly over time. And there are a bunch of things that could change or kind of affect the climate. The angle of the sun will affect your climate. How much sunlight you get will then determine how much heat you get from the sun and the temperature of an area. The likelihood of cloud coverage, air pressure, all of those things are going to go back to the amount of sun that an area gets and how that affects its location over time. That's really what determines climate. So in order to look at how climate changes based on solar energy, we have a slide about latitude. Now, my understanding is some of you have learned about latitude from social studies, but just in case you have forgotten what latitude is, we're going to watch a short little video on latitude.
It is estimated that the Earth is over 4.5 billion years old, and that modern humans have been walking the face of it for around 200,000 years. The geography of our planet has shaped the population patterns, available resources, industries, cultures, and nearly every facet of human activity during those 200,000 years. Geography is a study of the physical features of the Earth and how they affect the humans who call the planet home. Physical features include landforms like valleys, mesas, mountains, deserts, volcanoes, and canyons, along with waterforms like lakes, rivers, and oceans. To pinpoint locations on Earth, geographers use either relative location or absolute location. Relative location is where a place is located in relation to another place. For example, the treasure is located around the rock, through the palm tree forest and near the open clearing. Absolute location is the precise point where a place is located on Earth. To find absolute locations on Earth, a geographer uses imaginary lines called latitude and longitude. Lines of latitude circle the Earth from east to west, while the lines of longitude circle the Earth from north to south. Geographers measure latitude and longitude in degrees. Each degree of latitude is about 69 miles, or 111 kilometers. Degrees of longitude work a bit differently. The lines converge at the poles and are widest at the equator, with a distance of approximately 69 miles, or 111 kilometers at that point. Lines of latitude and longitude intersect at right angles at the equator. The equator is the line of latitude that divides the Earth into the northern and southern hemispheres. At 0 degrees latitude, all locations north of the equator are written as n number of degrees. All locations south of the equator are written as s number of degrees. Lines of longitude begin at the prime meridian, which divides the Earth into eastern and western hemispheres. At 0 degrees longitude, all locations east of the prime meridian are written as e number of degrees. All locations west of the prime meridian are written as w number of degrees. People are using the lines to crisscross the world every day. Ships and airplanes need to use the coordinates to navigate the oceans and skies, while travelers use the lines of longitude and latitude to find specific landmarks. You can use the lines of longitude and latitude in your own community to go geocaching to find treasures hidden where you'd least expect it. Studying geography allows us to understand the reasons people live in various regions, how physical features affect the economy of communities, and on a larger scale, global political issues like border disputes, climate change, access to food and clean water, and the spread of diseases, just to name a few. Jumping into the world of geography is as easy as opening a GPS app on your smartphone and putting one foot in front of the other. So what are you waiting for? The world awaits.
Okay, so if for some reason you were not able to hear that well, or you want to re-watch the video, the link is at the bottom of the slide in the speaker notes. So you can just click on that link and it will bring up that same video. All right, so the video again just kind of reiterated what latitude is. Basically, it's a marker that shows distance from the equator moving north and then from the equator moving south. So anything above the equator is going to be north. Anything below the equator is going to be south. Now the equator starts at 0. So that is like when you're on the equator, you're at 0 degrees north or 0 degrees south. Anything above, you go closer and closer and closer all the way up till you get to 90 degrees north. And then if you're going down, you go closer, closer, closer down further until you are at 90 degrees south. So that's basically latitude for those of you who may have forgotten. We can use latitude, again, going back to the amount of sunlight that an area gets, how that determines its climate. We can use a measure of latitude to help us to figure out how much sunlight an area gets. So if an area is located at 0 degrees, that would be the equator, it's more likely to get sunlight. If we think back to kind of our astronomy unit, remember at different points of the year, the northern hemisphere will face towards the sun or away from the sun, southern, same thing, but the equator pretty much gets direct sunlight all year long. That's why people who live on the equator are going to get more sunlight, more heat. Generally near the equator, it's going to be hotter. For areas that are really close to the poles, either the North Pole or the South Pole, they are getting direct sunlight only for a short amount of time throughout the year. And then at some points of the year, they're getting absolutely no direct sunlight. So that's why areas near the North Pole or the South Pole are going to be typically receiving less sunlight, and it's going to be cooler there. So that's kind of the general breakdown. The closer you are to the equator, the warmer it is. The further you are from the equator, it's going to be colder because you get less sunlight. So again, we have unequal heating occurring. Areas near the equator get more heat than areas further away from the equator. And because we have this difference in sunlight, we can actually divide the Earth kind of into 3 different zones based upon how much direct sunlight each one gets. So our 3 zones are the following. We have the polar zone, which is areas north of 66.5 degrees north and south of 66.5 degrees south. So basically the areas of the North Pole and the South Pole. If we go back here, it's kind of anything that you see in the green or blue region, or even the purple. So at the poles, North Pole and the South Pole, the sun's rays are going to be the least direct. They're not getting a lot of sunlight, so they're not getting a lot of heat. Much of the area is going to be covered with ice and snow, which reflect the sunlight, and our temperatures are going to be lowest here. Kind of makes sense. And then the next one we have is the tropic zone. So if we go back to that picture, the tropics are anywhere you see that bright red orangey. And that would be at 23.5 degrees north and down, or 23.5 degrees south and up. So that would be at the equator, pretty much. Basically, at the tropic zones, we have the sun's rays are the most direct, and that's where temperatures are the highest. And if you look back at the map, we see this equator line kind of going through. Technically, there are 2 tropic zones, one right above the equator and one right below. But since the equator is just an imaginary line that's separating them, sometimes we think of the tropic zone as one big zone, the north and the south kind of chunked together, and it is kind of just one larger zone instead of 2 smaller separate ones directly next to each other. Finally, we have the temperate zones, and these are kind of like the in-betweens. That would be your area where it's kind of orangey yellow, kind of going up towards green. Same thing down here, orangey yellow, kind of going towards green. And basically at the temperate zones, it's in between. You get a medium amount of sunlight, you get kind of different temperatures all year round. And actually New Jersey is smack dab in the middle of the temperate zone. We have a latitude of about 40 degrees north, and 40 is kind of right in the middle of 23.5 and 66.5. So we are a perfect example of the temperate zone. We have all 4 seasons. At one part of the year, we get more direct sunlight. At the other part of the year, we get less direct sunlight, and then spring and fall is pretty much even for us. So we are a good example of a temperate zone. Basically, if you live closer to the poles, you're going to get less direct sunlight over the year, and it's going to be generally colder. If you are right outside of the temperate or the tropic zone, but you're still in the temperate zone, think like Florida, it's going to be warmer, but you still get a slight change with the seasons. So that's kind of the general rule for our temperate zones. In terms of what it looks like, polar zones, again, are near the North Pole or the South Pole. They have less amount of sunlight, and it kind of gets shared over a larger area. Temperate zones are in the middle. Okay, they get different amounts of sunlight depending on the year. Sometimes it's a lot, sometimes it's a little. And then tropic zone gets pretty much direct sunlight throughout the entire year, and that's why it's the warmest there. So we go from polar zone, cold, medium, hot, medium, cold. Okay. So that's our latitude zones. Not too much to kind of go over there. It again depends on geography and how close you are to the equator. Closer you are to the equator, more sunlight you get, it's going to be warmer. All right, so now we're going to talk about wind. And this is kind of what is a main cause of climate, or another determining factor of climate. Yes, sunlight determines the climate of an area, but wind can also determine the climate of an area. So basically, we have to go back to our air masses and fronts lesson. And one thing that we learned was that differences in air temperature and pressure will cause patches of air to move. Remember when we learned about high and low pressure systems? We learned that air will always go from high pressure to low pressure. So basically we have areas of warm, less heavy air near the equator. That's going to go up. That's our low pressure system. And we also have areas of cooler, high pressure near the poles. So I'm going to show you kind of what that looks like. I'll stop the share. Here we go. Okay, so let me see if I can make this slightly zoomed in. It'll do. So we have over here, air always goes from high to low pressure. We learned that before. Same thing's going to happen here. We have our polar zones are going to be colder air because they get less sunlight. And typically, if you have cold air, you're going to have higher pressure. That air is going to stay closer to the surface. When we're talking about our tropic zones, it's warmer there. They have more heat. It's going to be because they get more sunlight. So they're going to have typically lower pressure air. That means that the air is going to rise more frequently. Okay, so if we have two areas on Earth that are more prone to having colder air and higher pressure, warmer air and lower pressure, we can now start to think about how air is going to move across the globe, not just in, one part of the United States to the next, but globally, how is that going to look? So what I have here is kind of a image of the Earth. So up here, I'm going to label our zones. We have the polar zone right there. And then further down, we have another polar zone. Okay. Let's see if I can get this higher up. There we go. Okay. So we have a polar zone up top and a polar zone down at the bottom. We have our temperate zone, and actually I should grab we'll go with like a orangey peach color for that because it's kind of in the middle. We have our two temperate zones. And then we have our tropics. Again, since there's technically two, but they're right next to each other, we kind of think of one large one. Okay, so there's our tropics. This little dotted line is our equator that's going through. So like we said before over here, air always goes from high to low pressure. So in the polar zone, if it's over there, it's typically getting less sunlight. So it's going to be colder. And like we said, colder air typically has higher pressure. Okay, those two kind of go together. So that's our polar region. For our tropics, we have warmer air because they get more sunlight. And if it's warmer air, typically it's lower pressure. And again, think back to our high and low pressure systems. Low pressure systems typically brought warmer air. High pressure systems brought slightly cooler air. All right, so we have colder, higher pressure, warmer, lower pressure. If we know that air always goes from high to low pressure, which region would you likely think the air is going to go from? Probably the polar region because it's higher pressure. And which region is it going to move towards? The tropics because it's lower pressure. Again, if it goes from high to low pressure, polar zone has higher pressure, tropics have lower pressure. So that's why we typically see air moving from the polar region down towards the tropics. And again, that is usually cooler air from the polar region going down towards the tropics. And the same thing would happen down here too. Again, it's colder air, higher pressure. It's gonna go from the polar region up towards the tropics. Same thing down here. Ta-da, perfect. All right, so that kind of goes over how wind will move. Not only, we already knew kind of how it goes from one area to the next. It always goes from high to low pressure. But when we think about it globally, since the polar region is colder, and colder air is usually higher pressure, and since the tropics is warmer, and warmer air is typically lower pressure, when we have these difference in our latitude zones, globally, we're going to have air moving from the polar region towards the tropics. And that also explains why wind is typically cooler, why it creates that wind chill. So we'll go back to that slide, and that slide pretty much just explains exactly what I showed you on here, just in words. So, share my screen. Okay, so like we said, basically cold, dense air is going from the poles. It's gonna go and it's going to move up into the tropics where we have warmer, less heavy air, and that air is gonna move up. Over here, we can kind of see another picture of that. The low pressure moves up and the higher pressure takes its place. So again, that kind of describes wind movement globally. Additionally, down here it just says globally, colder, higher pressure air near the poles moves towards the warmer, lower pressure area near the tropics. Basically, this is a very important part that you want to know. Oops. My suggestion would be highlight this last little paragraph. That's going to be helpful for you when it comes time for a quiz or anything like that. All right, so that is wind and kind of how it moves air globally from the polar region to the tropics. Now we're going to take a look at one more way that wind can kind of move, and that's based on the Coriolis effect. So it's lovely to think that, okay, yep, it goes from the polar region to the tropics, super easy, it goes straight there. But unfortunately, that's not how it works. If we look back at my picture here, you notice I made kind of little like curly cues as the air was moving towards the tropics, going from the polar towards the tropics. It would be nice if it would just go straight down, but that's not the case because we have to account for the Earth rotating. So because of that, we actually get something called the Coriolis effect. And basically what that does is it takes those winds that move from the polar to the tropics, and it's actually going to change the way they move. So again, it says, remember, Earth's constantly rotating. We learned about that back with our astronomy lesson. As the winds blow from the north and south towards the equator, from the north and south pole towards the equator, their flow path is deflected by the Earth's rotation. So basically, you're going to have the winds kind of change their direction. It's going to curve a little bit. And let's see. Oh, let me get out of here first. Let's see. So on the next slide, we can kind of see a good explanation for this, or rather not an explanation, but the kind of underlying takeaway. When we're talking about the Coriolis effect, one thing that you absolutely have to know is that, yep, it changes the direction of the winds, and it also changes the direction that they go based on the hemisphere that you're in. So in the northern hemisphere, above the equator, it's going to go counterclockwise. In the southern hemisphere, below the equator, it's going to go clockwise. So what we're going to do is, I'll get out of here. There are two videos that I want to show you about the Coriolis effect. And then from there, we will kind of wrap things up. Again, if for some reason you're not able to hear the video, you can always, if you go to this slide, there's 2 links down here. We're just going to watch those 2 links in that order. Let me see. Nope, don't want this. Here we are.
What's going on here? Every time I throw the ball straight, it seems to bend to the side. No matter what I throw, no matter how straight I throw it, the ball seems to be curving. Maybe it has something to do with this. That whole time I was spinning, which is why it looks like I'm about to puke. That curve is created by the Coriolis effect. You may have heard that it makes water in the bathtub spiral down the drain a certain way, or that it determines the way a toilet flushes. That's actually wrong. Those are not caused by the Coriolis effect. But the Coriolis effect is what makes hurricanes spin, and it's the reason why Jupiter's Great Red Spot is spinning the way that it is. So what is the Coriolis effect? Well, it's what happens when objects moving in a straight line appear to curve because you are rotating. And it affects all kinds of things. It bends the paths of missiles and sniper shots. But how does it work, and how does it create hurricanes? Right now, it seems like the ball's curving, but let's take a look at what's really happening. My friends and I put together this little experiment using a sort of spinning seesaw. Here, the camera's standing still. It's just hanging from the ceiling. And watch what happens. From the moment the ball leaves my hand, it's just going straight. Let's watch that again, frame by frame. Keep your eye on the ball. You can see it travels in a perfectly straight line. But what if you're spinning with the seesaw? Look at what happens when you rotate the footage so the seesaw stays sideways and everything moves around it. Now let's follow the path of the ball again, but from this new perspective. The trajectory looks completely different. Now let's watch this one frame by frame. From this rotating perspective, it totally looks like the ball is curving. That's crazy because you already saw that exact same throw. Watch it again on the left. The ball is going straight, but on the right, when you're rotating with the seesaw, the ball really looks like it's curving. You might be thinking, why should I care? I don't spend a lot of time on a spinning seesaw or on a merry-go-round. But you kind of are on a merry-go-round. The Earth is constantly spinning. Have you ever seen someone in a movie making fine adjustments on their gun? Well, one effect they're correcting for is the Coriolis effect. The longest sniper shot, which was over 3,000 yards, would have had to correct for a 1-foot deviation due to the Coriolis effect. So how does the Coriolis effect create hurricanes? Hurricanes form when air rushes from all directions into a low pressure region. So imagine there's a low pressure region between the two of us. Air is going to rush toward the center. Let's see what that looks like from space, from our camera that's hanging from the ceiling. It's not spinning, so the air, or in this case the balls, are clearly going in a straight line. But if you're rotating with the Earth, or with the seesaw, you'll see the air bend to the right. In the northern hemisphere, this creates hurricanes with counterclockwise spirals. In the southern hemisphere, it does the opposite. It creates hurricanes with clockwise spirals. This storm on Jupiter, which is actually bigger than the Earth itself, has been spinning for at least 200 years, largely due to the Coriolis effect. So when you're in a rotating frame, the Coriolis effect seems to exert a very real force on objects. But there is no force. What you observe is just a result of your perspective. And you might be wondering, if this is simply a product of your frame of reference, then could other forces like gravity or electromagnetism also just be products of your frame of reference, of where we live in the universe or in the multiverse? For more on that, check out our video, Do We Live in the Multiverse? There are talking fish. And if you want to find out when new episodes come, click subscribe.
Okay, so that was that video. I'm actually going to let you, if you want to, you can watch that other video on your own. But again, it just goes over kind of why the Coriolis effect happens. Again, for us, the biggest takeaway that you need to know is that in the northern hemisphere, it goes counterclockwise, and in the southern hemisphere, it goes clockwise. And again, what does it do? It causes the winds to change their path. It's as simple as that. So basically, we're going to stop here for today. We've covered quite a lot. We've talked about what climate is. We've talked about latitude and how it plays a big part in determining the climate. Remember, if you get more sunlight, you're going to have warmer temperatures. If it gets less sunlight, you're likely to have cooler temperatures. And we have our 3 latitude zones. We have the polar zone, tropic zone, and the temperate zone. We talked about how wind moves globally. Basically, the poles, areas of colder, higher pressure near the poles, will move towards the warmer, lower pressure area near the tropics. And it doesn't move quite as easy as just moving straight from the polar region to the tropics. Because of the Coriolis effect, that Earth's rotation will cause the winds to kind of curve their path, and it will cause wind systems rather to move clockwise in the southern hemisphere and counterclockwise in the northern hemisphere. One last thing on this slide over here, there is a link to a pretty cool website. I'll show you what that looks like. I zoomed into the United States, but basically it shows you on a particular day, whatever day you open it, how winds are moving on Earth. So there's a little thing that you need to choose over here. It starts off as ocean. If you click on air, it'll show you kind of what the air is doing. And in an area where there is these white lines and we have green or even yellow, that shows a lot of wind, high moving or fast moving wind. In areas where it's just blue, there's pretty much no wind. So if we look around us, this is I took this video on Monday night. So we had those big thunderstorms kind of today and even into last night. So we can see near us in New Jersey, there's a lot of wind moving really, really quickly off of the coast. And it's also coming from this direction too. So we're kind of in an area where we're getting a lot of wind, which will likely cause bad weather. And we did get bad weather. If we look over here at our weather map, we actually have a bit of an occluded front coming through the area, which caused our really heavy thunderstorms and even potential tornado warnings or what have you. Another cool thing to look at on this website is areas of low pressure. Remember, we know that low pressure area goes from that area or from areas of high pressure towards areas of low pressure. So if you look up here, we have an area of low pressure. We also have an area of low pressure kind of in the southwest. And if we go back to the weather map, we can kind of see those areas as well. Low pressure here, low pressure up here too. All right, so tomorrow you guys will get another video to go over the rest of these slides. And don't forget you need to fill out your exit pass. The exit pass will just go over these 9 slides that we did today. All right, again, if you have any questions, please let me know. I will be more than happy to answer them. And I'll also put I'll kind of scan it, take a picture of it, and put it up on Classroom as well as a reference for you guys. All right, have a good one.